Well, thank you. This is my first of these meetings, so it's been, well, despite the unusual time, it's been a really fun meeting to attend. So I'm glad I signed up. So I wanted to talk about some of the work that me and my collaborators have been doing. It's kind of ongoing work. Although the title and the abstract are about this modeling the initial morphology of complex craters with Perlin noise, I thought it would be useful to kind of set up the problem and show why it is that we're working on what we're working on. So really what we are trying to do is understand crater equilibrium and what are the processes involved in setting the observed equilibrium. So right here I showed like the textbook model for crater equilibrium that comes from Jay Malash's textbook. The sort of idea behind what kind of equilibrium you get really fundamentally comes down to what does the production function look like. And there's kind of two ideas about what equilibrium looks like depending on whether you've got a steep or a shallow production function. So in a steep production function, shown on the left, that was modeled by Galt physically and back in the Apollo days to try to observe, understand the observed craters on the mare that they were seeing for the first time. In a steep production function, when the steep branch hits this equilibrium line, whatever sets that, it rolls over to this equilibrium size distribution, which has a cumulative slope of -2. There's a idea that if you have a shallow size distribution, you are in a different kind of regime where cookie cutting dominates. That's where craters overlap each other and basically cut out the the idea is that you get this sort of quasi-equilibrium where you retain the production function slope, whatever it is, and you kind of bounce up and down in this sort of quasi-equilibrium state. So I want to first tackle the sort of steep slope end and the mare craters, because we just had a paper on this last year. It's been long known that craters at this scale are degraded diffusively. So that is that over time, these small impacts sort of redistribute material around and soften the terrain, and the craters kind of melt away over time in this process called topographic diffusion or soil creep. And you can describe topographic diffusion with a couple of parameters, mainly the diffusivity, but I prefer to use the degradation state. Degradation state is just the product of diffusivity times time. And it's useful for cratering to kind of get rid of the time component. You don't have to worry about the changes in the production rate when you work in degradation state. And this was modeled back in the Apollo era, Larry Soderblom and Ross in the late 60s, early 70s. All right, so on mare-scale terrains, this sort of diffusion-dominated equilibrium is actually very obvious, and it was observed back in the Apollo days. So here's an example of sort of a case of diffusive equilibrium from Stuart Robbins' big crater counter paper. And these are Caleb Fassett's counts of the Apollo 15 site, which shows this classic diffusive equilibrium. So you reach you have this -2 slope size distribution of craters. The production function has a slope more like -3, 3.1 or 3.2. The equilibrium value is about 1 to 3% of this so-called geometric saturation, which is a hypothetical upper limit based on the the way circles can pack into a surface. 1 to 3% is pretty standard. You see a few percent, maybe 5%, some variations, but the slopes tend to stay around -2. We developed a model, actually a couple of models, to actually understand this process, to understand why is it that equilibrium reaches this sort of few percent of geometric saturation. And we did this with two methods. We have a numerical modeling tool, CTEM, which is a landscape evolution model. But we also have developed some analytical models, primarily based on some of the work of Larry Soderblom and others back in the 70s, to really understand this. And there are two sort of free parameters of the model that we actually can use to understand this. And they're both written in terms of this degradation state. And the first one is the visibility function, K sub V. And what this is this tells you how much diffusive degradation it takes to degrade a crater of a given size before a human can no longer recognize it. And it basically is the encoding of this human element. So I've got you know, a sampling of crater counters and other kinds of counters on the right here. And the visibility function basically tells you, you know, how much degradation a crater can withstand before these people can recognize them. And this is a united quantity, so it's in units of length squared. So basically, the idea is that larger craters take more degradation to get rid of. So I've just got a test case here where I've got a bunch of craters of different sizes, and the small craters go away faster than the bigger ones. And you can express this as a degradation function being a power law. And it's as long as the craters are self-similar, that means that the shapes are the same at all scales, then you expect the exponent of that power law to be 2. So that it takes, you know, basically it takes the square of the radius or the diameter of the crater more diffusive degradation to get rid of a bigger crater than a smaller crater. All right, and then the coefficient, the sort of the number out front here, we can derive from a crater counter study. So, and it turns out that there's the variation in human crater counters can be expressed in the variation in this parameter out here. So this parameter was set by an undergrad who worked in our lab named Brian Howell, and who pretty much matched Caleb Fassett's counts of that Apollo 15 site. All right, the other side of the coin is the degradation function. This tells you how much diffusive degradation each crater contributes to the surface. So every time a crater forms, it degrades the surface in a very complicated way across a region. And this encodes all the different ways in which a crater can degrade the pre-existing surface. So ejecta burial, seismic shaking, ballistic sedimentation, cookie cutting. These can all be encapsulated in this, this kind of function. Again, it's a united quantity in terms of the degradation state. All right, so one of the things that we did was to show that if you carefully kind of work through a model for all the different ways in which you can imagine a crater degrades the surface, including the cookie cutting and the burial by ejecta, which is the thing that people hypothesized back in the Apollo days was dominating this, and kind of work through all the different processes at work, and then you model it both analytically and with a numerical model, you get something that shows that it's not enough. So if you just include ejecta burial and cookie cutting, all of the things that are kind of obvious about the cratering process, you should expect to see an equilibrium crater distribution that's much, much higher than the observed value. And you get a surface that's much rougher and doesn't really look like the real lunar mare. And you can express this as what degradation function you actually need to match the constraint versus what you actually get with things like proximal ejecta burial and cookie cutting, which are the obvious things that are degrading craters. You see there's a couple order of magnitude offset. You actually need a lot more degradation by the craters in order to match the observed degradation state and the equilibrium value of the craters in the mare. All right, so what we found was that after you go through a lot of different ways of thinking about the problem, and there's a whole kinds of details in this very big paper. What we found was that what seems to be dominating this equilibrium crater distribution, what sets equilibrium on the mare scale, is what we call energetic distal ejecta, which really is just a fancy way of saying secondaries and secondary processes. You need a very wide, large spatial scale process where every crater is contributing some small amount of degradation over a very, very large surface, and it has to be this heterogeneous, spatially heterogeneous sort of pattern. And I can go into more details about why we came to that conclusion if you'd like later. But this really says that secondary craters in rays are really what's dominating the degradation of sort of tens of meter scale features on the lunar surface. And that -2 slope really of equilibrium has a lot of important implications about what kind of processes there are. They have to be tied to the production function really strongly. All right, you can see more details in this paper that came out last year. All right, so now let's move on to the highlands, which is really where we want to go next. So we learned a lot about the lunar mare. If we move over to the highlands, the heavily cratered, most ancient heavily cratered highlands, we get about a 3 orders of magnitude increase in size scale. The total cratering is much higher. The character of the surface is different. Morphology of the craters is different. You can see that there appears to be a lot more overlap, a little bit less, much less diffusion. There are other kinds of morphological features. And we don't really understand how equilibrium works at this scale, whether it's been long controversy, whether or not it's even equilibrium or not. So, you know, I talked about the textbook example where you have a steep versus shallow size distribution, but you know, the highlands are really neither. The slope of the production function shown in this blue line here kind of goes from steep to shallow and steep again. It's kind of wavy. And so what really do you get? So people really have been looking at this and numerically, and most of the conclusions have been it's something more like this than like this. Just as an aside, Bill Hartmann has long had this hypothesis that there's really one kind of equilibrium. It's called empirical saturation equilibrium. It's a size distribution that kind of fits from the small end to the big end with a slightly shallower than -2 slope. This is based on just observing that you can kind of fit a line from the kind of highland scale craters to the mare-scale craters, and everything kind of fits along that power law. All right. So one of the things we can start with is say, okay, well, let's just take what we learned in the mare and apply it to the highlands. What do you get? So we're going to take all the constraints on the visibility and degradation functions that we learned at the mare scale and just going to naively apply them on the highlands and just see what happens, knowing that this is not the end of the story. All right. So what we do is we set the degradation function, the visibility functions exactly as they were for the mare. So everything's scaled up, of course. You know, it's not the exact numbers, it's the power laws that you scale everything up to the larger size. And what you see is that you get a very different kind of surface, a much smoother kind of not really realistic looking surface, and you get way fewer craters than we actually observe. So something's wrong here. Now, it could be the visibility function. Of course, the visibility function tells you something about the morphology and how visible the craters are. And we should expect a couple of things. First of all, the complex craters are shallower, so might expect that the visibility function would be less than that for the mare. But it's also in some ways easier to see big craters, especially the basins, because we actually see them in more than just visually. In fact, we might even have a complete record of lunar basins above 250 kilometers. We can also turn that analytical model around that we developed in our paper and actually ask what should the equilibrium look like? Can we actually fit an equilibrium solution that kind of matches the craters we see above, you know, at the large end and the craters we see at the low end? And there's a lot of unknowns in this. But we kind of came to sort of a best fit solution. We can kind of fit an equilibrium solution that kind of matches. If we hypothesize that there really is an equilibrium signature in the craters here by just shifting around the degradation function slope. Of course, we don't get really anything that looks exactly like the highlands. But what we find from this exercise is that in order to kind of match or at least come close to matching the highlands, you need this degradation function to roll over. That means that, kind of oddly enough, the large craters actually degrade the surface less relative to their size than the small craters. And that's kind of a surprising counterintuitive result, but it seems to be what you need. Big craters are, you know, for their size, less degrading than small craters. And we published this I had a visiting grad student, Christian Riedel from the Freie University Berlin came. We have a paper that just came out showing this. But again, the morphology here, the sort of character of the terrain doesn't really look right. We can kind of get close, but there's a lot missing from this. One of the key steps in order to really get this right is to get this morphology of craters better. So you can see here, this is the real crater Copernicus. This is what our CTEM, our numerical model, sort of produces right now, which is a highly simplified crater. So I've been working on a better method of this using this cool technique called Perlin noise. So Perlin noise is actually really well known in computer graphics. It's used in video games, and it's used in like Pixar films and various things like that. And it's a way of reproducing sort of naturalistic textures in a very algorithmically simple, fast way. And basic idea behind Perlin noise is you get this sort of quasi-periodic function that has some properties of it. It's just a mathematical function, sort of a pseudo-random sheet, and that you provide a bunch of parameters to it, you layer them together, and the end result is this thing that looks like a mountainous sort of rough terrain. I actually generated this with our CTEM test code, and you can actually make some really interesting, very realistic looking terrains with very little computational costs. It hardly costs you anything to do something that looks really cool. So what I've been working on is to analyze the Perlin noise layers in a way in order to constrain them against observation. So you can do some power spectral analysis, take a basic Perlin noise model, figure out the power spectral density, and you can fit models of things like the Hurst exponent to kind of the model terrains you get. And then you can match those to real terrain. So I had an undergrad in our lab last summer who collected a bunch of examples of DEMs of fresh complex craters. So here's Copernicus, for instance. And we can take Copernicus apart and, let's say, look at the ejecta blanket, figure out what kind of texture that you actually get on the real ejecta blanket, fit a PSD model to it, and then build a Perlin noise-based texture that actually matches the properties of that. So this is a texture that has the same spectral properties as the ejecta blanket of Copernicus. But there are a lot of other parameters at work here. So we've got things like the rim shape, the scalloped rim shape, the terraces, the central floor texture, the central peaks. All these things, it turns out, with a little tweaks, you can actually model really, really well with a Perlin noise-based approach. So what we're doing right now is kind of looking through a representative example of the freshest big craters, which are not always easy to be able to pull out. So here's just some of our test craters that we're working with at different scales. So Harpalus, sort of near a transition size, Copernicus, Schrödinger, Oriental. And we've got a sort of catalog of these DEMs that we're kind of working with, and developing a kind of a Pike 1977 kind of thing where we look at how the parameters change with different craters, and ultimately want to be able to find constraints on equilibrium. And I really answered the question is, are the highlands craters in equilibrium, and what does that look like? So I'll stop there and I'll answer any questions you have. Thank you.
Great, thank you, David. That was very exciting for me anyway. Stuart, are you going to relay the questions?
So Clark Chapman's first question, what physical processes are simulated by Perlin noise?
That's a great question. Really, it's not simulating any kind of physical process. You can kind of think of it as mimicking the sort of fractal nature of reality, of natural surfaces. So natural surfaces have this sort of fractal character, right? You have sort of roughness at all scales, and you can characterize that with these power spectral density and things like the Hurst exponent. I think there's a lot of work in landscape evolution and geomorphology and sort of modeling these kinds of things. So we're not actually modeling any physical process. What we're doing is just sort of empirically matching what we observe in nature. And that's kind of the tack I'm taking is looking through the catalog of real lunar surface features, extracting these sort of parameters and then mimicking them with the code. And for a code like this, or a landscape evolution code like CTEM, I think that's really the approach you need to take, because we have to, when we do this, the full scale simulation, we're producing millions of craters. And so what we're really trying to do is do something really fast and quick that gets as close to something that's realistic as possible, but we can't afford to actually go through and model the physical processes. Now, it would be really cool to see if there's reasons why, for instance, the texture has this Hurst exponent as you move to different, size scales. But right now we're just trying to kind of mimic.
Clark notes, but craters are fractal. Real terrestrial features are fractal for other physical reasons. Yes,
that's true. But I don't really care at this point about what the physical reasons are, just trying to mimic what it looks like. So once we get the sort of catalog of what these parameters how these parameters change with scale, then you can maybe start working out what are the things that set that.
All right, Bill McKinnon asked, can you talk more about how large craters don't have the same degradation effects, scaled, as small ones? As you say, it seems rather counterintuitive.
Oh yeah, so this is hard to explain. I try my best. So it is counterintuitive, but this is the result that we get. So if you think about our exercise of taking what we learned at the mare-scale and just scaling everything up, we got this like super smooth, flat-looking terrain. So when you just take the amount of degradation that a crater is producing and just naively scale it by its size squared, which is by units, the unit analysis, that's what you expect to do. Get these dashed lines here. So these are the degradation functions. This is, remember, characterizing how much degradation any given crater produces over a region. And these F sub E really tells you about the size, the spatial scale. So this is a degradation over 3 times the crater radius, and this is 10 times. So you need less for a bigger area. And if you just take the mare constraints and just scale it up, you'd follow this dashed line. But when you actually do the simulations or do the analysis, the analytical model for this strong a degradation function at these scales, you get this super smooth, flat-ish looking kind of diffused away terrain, which is not what we observe in nature. So you just tweak the model, and you need that degradation function to be orders of magnitude less powerful for these large craters. So from an absolute sense, the bigger craters are degrading the surface more, but relative to this sort of natural d squared scaling, they're producing a lot less.
Okay, one very quick question to end with, because we need to move on. Can we get this is from Ankush, can we get an idea about regolith thickness by small crater properties like depth or ejecta?
Yeah, there's a lot of people have done this. There's actually an interesting thing that I've found, and Caleb and I have talked about this quite a bit, that when you look at the equilibrium size distribution of mare-scale craters, there's kind of a, if I can see it here, there's kind of this weird steepening that occurs. It's kind of really subtle, but right around about a few meters, 10 meters, the equilibrium distribution gets just slightly steeper than -2. And it turns out a lot of, if you just look at through the counts from that Robbins et al. 2014 study, you kind of see this, that there is a sort of very subtle steepening that occurs for craters less than a few meters. We've speculated about what that might be, and it could potentially be a change in the properties of the regolith at that scale, that something's happening that's not scale independent. So the -2 slope is really a consequence of everything being scale independent. The morphology is being scale independent, and the regolith properties and the degradation, all the things being scale independent. So something is breaking the scale independence, and there's a scale dependence down, making things different at the few meter scale.